Hello, students, can you hear me?
Yes, sir.
Yes, sir. Excuse me, sir. Excuse me, sir.
My M6, what do you want?
Ma'am, it's about
Hello?
regarding PPT, ma'am. I have a doubt about physics PPT. I want to ask sir about that.
Students, can you hear me?
Yes, sir. Yes, sir.
Hello.
Yes, sir. We are able to hear you.
Okay. So, have you done your assignment? Have you finished your assignment on problems on in module 2?
Yes, sir.
Hello.
Yes, sir. We have finished it.
Okay. It seems everybody is muted. Okay, so if you have any doubts, please write to me or message me so that we'll discuss again these problems. We have discussed some few of the problems from question bank in the previous classes. So I have given on other assignments to you. Okay, so if you have finished, please scan them and send to me. Or if you have any doubts, please let me know. So today we will move on to our next module, that is fiber lasers and fiber optics. So today I'm going to discuss about lasers. So I'll give you an introduction to lasers. So the topic we are going to cover is introduction to lasers, and we expect to find out what is the difference between normal light and laser light, and how does this make what is the mechanism of lasers, what is the key point in the operation of the lasers. Okay, so this aligns with the course outcome CO5. Okay, so what is a laser? Laser is it's an acronym. Actually, it's an acronym for Sunil. Sunil, you can unmute and speak. Sunil, do you have a doubt?
No, sir, it has suddenly clicked, sir.
Before slide? This one.
Sir, doubt ఏం లేదు సార్, సడన్ గా క్లిక్ అయింది సార్.
So laser is an acronym for light amplification by stimulated emission of radiation. Okay, it's not an amplifier, but it is a generator of light. Okay, so in 1916, Einstein has given the key concept for this. Okay, so he had an idea for stimulated emission of radiation. Okay, so we'll see what is stimulation of emission of radiation by, in our class in the next slides. Okay, so in 1954, C.H. Townsend he had put Einstein's theory into the practical level, and he had developed something called maser. Okay, which is instead of light, here it will be microwave amplification by stimulated emission of radiation. So he applied this stimulated emission of radiation concept given by Einstein to microwaves, and he developed a device called maser. And in 1958, Shallow and Towens they extended this theory to light, and P.H. Myman he built the first laser device in 1960. The first laser is a ruby laser, which is a solid state laser. So in 1916, the theory was developed by Einstein, and by 1954 it was applied for microwaves, and a device was developed that is called maser. And in 1958 it was extended to the light, and they developed a first laser that is called a ruby laser, which is a solid state laser. We have different types of lasers. One is solid state laser, that is ruby laser first, and in 1961 they developed a gas laser. The first gas laser is helium neon laser. Okay, and now we have different types of lasers, semiconductor laser, and different. Okay, so they are extended to semiconductor devices. Okay, so we have different types of lasers now. Okay, but what is the basic principle behind that? How does this laser comes out? So to understand that, first we need to understand the radiation interaction of the radiation, that is the radiation of energy with matter, or the interaction of light with matter. So for that we'll just go through that. So when a light travels through a medium, it undergoes absorption and scattering process. That is, light absorption means the transfer of energy from light to atoms, and light scattering involves change in the direction of travel of waves. Okay, so it is simply when light traveling through a medium, either it gives the energy to atoms, or it gets deflected by the atoms. Okay, so because of these two processes, light intensity decreases with the distance in the medium. So as long as the distance the light travels, the more distance, it becomes less intense. Okay, so there is another chance when light interacts with the atoms. There are two chances. One is light can give energy to the atoms, or atoms can give energy to the light. Okay, so the second process, that is atoms giving energy to the light or to the radiation, cannot be explained with the quantum mechanics. It cannot be explained with the classical mechanics. Classical mechanics can explain how the energy is absorbed by the medium from light, but it cannot explain how energy is given to the radiation. Okay, so this can be only explained on the basis of quantum mechanics. So let us understand what is this quantum mechanical process that involves in atom giving the energy to light. Okay, so this actually what happens is this transfer of energy. When the energy is given to the light, then the light amplifies, right? So energy is given, so the amplification of light should happen. So a light amplifier can be further converted into a source of light having superior characteristics compared to traditional sources. That is, like when you're giving the energy to that, so it becomes another source for the light radiation. Okay, but the only thing is we should be able to give some particular characteristics. We should be able to develop some particular characteristics when compared to the traditional light sources. Okay, so this becomes a laser. That's how we develop a laser. So a laser is a monochromatic coherent light source that depends on quantum processes for its operation. So what do you mean by monochromatic coherent light source? What do you mean by monochromatic? Monochromatic means all the waves, that is all the photons. So we know that light consists of photons, right? Light is nothing but a stream of photons. So all these photons will be having the same energy or in the same phase. Okay, they will be all in the same phase and coherent. That means they will have all the monochromatic is they all have same wavelength or the same frequency, and coherent mean by coherent is they all have the same phase. Okay, they are all in the same phase or they'll have a constant phase difference. We when it comes to coherence, usually we'll say that all the wavelengths, all the waves are in same phase or they have a constant phase difference. But here the coherent in lasers means they are in the same phase. Okay, so first we'll understand what is this quantum process that requires for the operation of lasers. So consider a material medium is composed of identical atoms or molecules, each of which is characterized by a discrete allowed energy states. That means we'll just consider a material medium which have all the atoms. So all these atoms can have, as we know that all the atoms can have different energy level, different energies. So they are populated in different energy states. Okay, so when there are energy state, when they are populated in different energy state, so an atom can lose energy and go to a lower level state. Okay, so let's say there are some different levels. So when one particular atom which is in an energy state and it can lose energy and can go to a lower energy state, or an atom which is at the lower energy state can gain energy, it can absorb energy from the radiation and it can go to a higher energy state. So this kind of jumping of atoms or molecules is called transitions. Okay, so the kind of jumping from one state to another state is called transition. Okay, now for simplicity, let us consider two states. Let us consider two energy states which are having energy E1 and E2. Okay, and let's say E1 is less than E2. Okay, so E1 is called, since E1 is less than E2, E1, let's say E1 is the ground state. Since we are considering only two states, so let's say since E1 has the lower energy state, so that will be a ground state, and E2 is an excited state. Okay. Now, as the atoms of the, so usually atoms, whereas we have discussed in our earlier classes also, so most of the energy, most of the atoms or the particles, they tend to be in a lower energy state so that the system will be in equilibrium. Okay, so more, let's say the most of the particles, where most of the atoms will be in ground state, or there will be few atoms in the excited state. Okay, so the number of atoms per unit volume at an energy level is called the population density. Okay, so the number of particular atoms in a particular state, or we call them as population. What is the population of atoms in the energy states, or the number of particles, or the number of atoms in the energy state? But the number of atoms per unit volume, as we know that when we are dividing any particular quantity with a unit volume, with a volume, that we call it as density. So here the number of atoms per unit volume is called the population density. So let the populations at the two energy levels E1 and E2 be N1 and N2. Okay, that means like there are n1 particles. So here it's not the population density we're talking about. We're talking about a population, that is number of atoms in the energy levels. So let's say n1, there are n1 level atoms in E1 level, energy level E1, and n2 atoms in energy level E2. So as I said, under normal conditions, higher the energy, lesser is its population. So most of the particles tries to be in a lower energy state so that the system will be in equilibrium. So in a normal condition, it will be always N1 will be greater than N2. Now let's say a monochromatic radiation of frequency nu be incident on the medium. That is, we are shining the medium with a particular light source, okay, which is having a frequency nu. Okay, it's a monochromatic. That is all the wave. So all the photons will have energy frequency nu or the energy h nu. Okay, so we know that. So here the next step here we can see that. So light is nothing but a stream of photons. Okay, so it will consist of the energy of the each photon will be h nu, since nu is the frequency, where nu is the frequency of the radiation. Okay, now if h nu equals to E2 minus E1, that is, if the frequency, if the energy of the photon equals to the difference of the two energy states, then the interaction of radiation with the atoms can lead to three distinct processes. Okay, that is absorption, second one is spontaneous emission, and third one is stimulated emission. Okay, so there will be three distinct processes which can happen if the energy of the photon equals to the difference between the two energy levels. Okay, now let's see what are these processes. So when a photon of energy, so you can see from this figure, when a photon of the energy h nu incidents on the medium, an atom residing in the lower energy state E1 may absorb the incident photon and jump to the excited state. That is, now there is an atom which is at the E1 level. Now when there is a photon is incident, which is equals to the difference between the two energy levels, then this particular atom absorbs this photon and it jumps to the higher energy level. Okay, that is E1 to E2. This particular process, that is jumping, that is transition of the atom from lower energy to the higher energy due to the absorption of a photon, is called stimulated absorption. That is the, here why it is called absorption, because the energy is absorbed by the atom. Okay, that's why we call it a stimulated absorption or induced absorption, simply an absorption. Because why it's simply absorption, because if there is no energy incident with here, this particular particle can never go to the higher energy state. Okay, but of course, if you increase the temperature, that is different story. So if you increase the temperature, the atoms will gain the energy, gain the thermal energy, and then they'll go to higher energy state. So that is a different story. But here, we're just simply talking about the interaction with the radiation. Okay, so there are this particular process is called absorption. Okay, now the probability that an absorption transition occurs is proportional to the density of photon density rho of nu. That is, what is this photon density? Here is the number of photons per unit time. Okay, instead of, usually this is a photon density, or we call it as photon intensity also. That is the number of photons per unit time. Okay, in some textbooks they call it as photon intensity, and some textbooks they call it as photon density, but both of them are same. Okay, so as you can understand, this is what happens. No, so if there are more number of photons, then there will be more number of atoms will be, and more number of atoms will absorb these photons and goes to the higher energy states or jumps to the higher energy state. So it's a very it makes very senseful that is the probability that an absorption takes place should be proportional to the photon density. Okay, so P12, that is P12 stands for the jumping off or the transition from level 1 to level 2. Okay, so P12 is proportional to rho of nu, or P12 equals to B12 rho of nu, where B12 is a constant of proportionality, and it is also known as the Einstein coefficient for induced absorption, or Einstein coefficient for stimulator absorption. Okay. Now we have another process, that is spontaneous emission. So we have seen we said there will be three distinct processes. So we have seen what is an absorption. Now let us go to spontaneous emission. So in spontaneous emission, atoms in a material have natural tendency to seek out the lowest energy configuration. Okay, so hence the higher energy states are usually unstable. So unstable, what do you mean by unstable is the atoms, most of the atoms will not stay in that higher energy states. So they will naturally lose the energy and moves back to the lower energy states. So they will jump from the jumps to the lower energy state. Therefore, the excited atoms, so here the atoms which are either due to the absorption process, these atoms will go to the higher, transits to the higher energy states, right? So these atoms, these excited atoms do not stay in the excited state for a relatively longer time. So they cannot stay in the higher energy state for a longer time. So they tend to return to the lower energy state by giving up the excess energy. So here the energy, as we have seen that E2 is greater than E1. So they'll lose the energy and they return to the lower energy state, and they release the energy in a form of a photon. Okay, they release the energy in form of a photon. So the energy of that particular photon, released photon, will be h nu, and that is equals to the difference between the two energy level state. Okay, that h nu is equals to E2 minus E1. Okay, this particular emission is called spontaneous emission, or okay, so this can be happen. I'm sorry. Also, this kind of energy, so losing the energy from high energy state to lower energy state, can be two types. That is, one is spontaneous emission or stimulated emission. Okay, so this spontaneous one, first we'll talk about spontaneous emission. That is, when there is an atom in the higher energy state, it can lose the energy in form of photon and transits to the lower energy state, but it is done on its own. Okay, so that is, the excited atom in the state E2 may return to the lower energy state E1 on its own, out of the natural tendency to attain the minimum potential energy condition. Okay, so usually, as you said, most of the atoms will tend to have lower energy state so that they can be in a stable state or the equilibrium state. So they simply lose the energy and comes to the ground state. Okay, and they lose the energy in terms of a photon. Okay, this emitted photon, as is just discussed, will have a energy h nu that equals to E2 minus E1. So this type of emission, this type of photon emission occurs without any external impetus, is called spontaneous emission. Okay, here the photon energy, the basic story is the atom is losing the energy in form of a photon and transiting to the lower energy state on its own. Okay, this type of transition, that is when it happens without any external observation, or any external perturbation, is called a spontaneous emission. Okay, But the problem with the spontaneous emission is it occurs randomly. Okay, so the probably it occurs randomly. We cannot have any control over these spontaneous emissions. Okay, the probability that a spontaneous emission occurs, that a spontaneous transition occurs, depends only on the properties of energy states E2 and E1, and it is independent of photon density. Because here it is the atoms are moving to the lower energy states because of their natural tendency. Okay, so higher the energy, they'll have it, the difference between E2 and E1. If there is a higher energy difference, then it depends upon the more the unstable the higher energy state is. Okay, so it is equal to the, so what it is, this probability should be equals to the lifetime of level E2. Lifetime of level E2 means how much time that atom can stay in energy level E2. Okay, that is what we call lifetime. So it depends upon the lifetime of the energy level E2. Therefore, this probability of spontaneous emission, that is from here we can see that P21, that is probable emission or transition from second level to the first level, and that is a spontaneous. Okay, that equals to the A21, where A21 is the Einstein coefficient for spontaneous emission. Okay, and as we just said that it depends upon the lifetime of the energy level E2. So here 1 over A21, that is A2 inverse of the A21 gives the lifetime of the upper state. Okay, that is E2. Okay. So here, as I said, the process of spontaneous emission is essentially probabilistic. Okay, so it's a random process. Okay, the atom, it's on its own, it is deciding whether it decides whether to leave the higher energy state and goes and reach the lower energy state. Okay, we don't have any control over the this spontaneous emission. Okay, so here the problem is, as I said, the problem is we cannot find out at exactly what time this transition happens, that is the instant of the transition or the direction of the emission of the photon. So when the process is happening, so it emits when the energy atom is transiting from the higher energy state to the lower energy state, the direction will be, the direction of the emission photon is not in our control. Okay, and what is the phase of the photon that emits, or the polarization state of the photons, or all are random quantities, so that we do not have any control over that. Therefore, the light generated by the medium will be incoherent, since it does not have a particular, it does not, all the photons are in different direction. The emitted photons will be in different direction, and their polarization state will be completely different from each other. So the light generated by this medium will be completely incoherent. Okay. Now let us move to the stimulated emission process. So in stimulated emission process is another way of actually moving another way for the atom to move to the lower energy state. Okay, so here a photon of energy h nu equals to E2 minus E1 can induce the excited atom to make a downward transition by releasing the energy in the form of a photon. Okay, so here in absorption process, what happens is, in absorption process, the energy instant photon interacts with the lower energy state atom, and it raises to the higher energy state. Whereas in stimulated emission, the photon interacts with the higher with the atom, which is already in a high energy state, and induces it to move to the lower energy state. Okay, but in this process, what happens is this instant photon is not absorbed by the higher energy atom in the higher energy state, but it simply interacts with this and releases and transits to the lower energy state. In this process, In this process, the energy of the atom loses the energy and produces another photon. Okay, produces another photon. The important thing here is the energy, the emitted photon, because of this particular process, will be in the same direction with the, which is in the same direction as the instant photon. Okay, so this phenomena of forced emission of photons is called induced emission or stimulated emission. Okay, so here in here the main difference is from spontaneous emission. Here is the spontaneous emission, they simply depends upon the lifetime of the higher energy level, and the atom will have a tendency to go to the lower energy state. So the atom decides on its own to lose the energy and emits a photon. Okay, this is what we call a spontaneous emission. Whereas in a stimulated emission, the atom in the higher energy level interacts with the instant photon and loses its energy by emitting a photon. Okay, but this emitted photon will be in the same direction of the induced or the incident photon. Okay, this particular mechanism was predicted by Einstein in 1916. Okay, it is predicted in 1916. He said to establish the equilibrium between the atoms, there should be a particular this particular stimulated emission should be existed. So that's what he said. That's what he predicted in 1916. But there was no particular proof for that. But still, 1954, when Towens and their collaborators devised the measure. Okay. So the probability. So what is the probability for a stimulated transition? Is so this particular probability for stimulated transition depends again on the photon density. So similar to the absorption, this P21 stimulated also depends proportional to the photon density, instant photon. So if there are more number of photons are incident, then there will be more number of atoms from the higher energy state interacts with them and loses their energy and reaches to the lower energy state. Okay, so naturally P21 stimulated is proportional to rho of nu, and P21 that is we can take equals to B21 rho of nu, where B. So you can see that we have used both A and B, where B is used for both stimulated emission and stimulated absorption. So if it is B12, that is from one lower first stage to second state, that is from lower state to the higher state, then that is absorption. If it is from 2 to 1, that is from the higher state to the lower energy state, then it is a emission. Okay, so B is used for stimulated and A is used for spontaneous emissions. Okay, so here B21 is also a proportional constant, and it is known as Einstein coefficient for stimulated emission. Okay. So far, are there any doubts? Students?
No, sir.
Hello?
So once you repeat the last one.
So guys, can you hear me?
Yes, sir. We
Are
can
there
hear you,
any
sir.
doubts as of now?
So repeat the last one.
No? So then I'll continue. last slide, this one or this one? Do you mean 18th slide? Okay. This one. So here the probability that a stimulated transition occurs. So what is the probability for this transition occurs? That stimulated transition, that is stimulated emission can occur, depends upon how many incident photons are there, right? Photon intensity, that is the intensity of the light. So if the intensity of the light is high, that is the number of photons per time is high, then more number of atoms which are in the higher energy state have a tendency to interact with this light, and they'll move to the lower energy states. Okay, right? That is what we expect, right? If there are more number of, so what is stimulated emission? The higher energy atom in the higher energy state interacts with the incident photon and loses energy in the form of a photon and reaches to the lower energy state. Now, if there are many here, for example, we have just taken one photon and one atom in the higher energy state, but usually there will be many number of atoms in the higher energy state. So if the intensity of the photon is very high, then there is a high chance of getting the more number. There is a high chance of for the atoms to interact with these photons and reaches to the lower energy state, right? So the probability for occurring probability for stimulated emission to occur is proportional to the photon intensity or the density. So that we have, this is proportional to rho of mu. So we have just taken P21 stimulated equals to P21 rho of mu, where B21 is simply a constant of proportionality. Okay, and we call this as Einstein coefficient for stimulated emission. Now here we have used in these three processes, we have used three coefficients. These three are called Einstein coefficients. To simply remember, B is used for stimulated emission or stimulated absorption. If it is from B12, that is from lower energy state to the higher energy state, then it is called Einstein coefficient for stimulated absorption. If it is B21, that is from higher energy state to the lower energy state, then it is Einstein coefficient for stimulated emission. If it is A, so we have here, this is B21, and we have spontaneous emission, we have, sorry, for spontaneous emission we have used A. Spontaneous, this is emission, so A21, that from higher energy state to the lower energy state. Okay, and for spontaneous stimulated absorption, we have used B12, that is from lower energy state to the higher energy state. Okay, these are called Einstein coefficients for either induced absorption or stimulated emission. Okay, so now do you understand that? Who is that? P5, I think, who was this out? Okay, right. Now, what are the characteristics? See, we know that this incident photon, we know because it is in our hand. Okay, so we can control this one. But what are the characteristics of these emitted photons? So that we'll see. So these characteristics of emitted photons are, the emitted photon has exactly the same energy, same phase, polarization and direction as the incident photon. Okay, so these emitted photons will have the same energy, because that way only if h nu is equals to E2 minus E1, then this particular atom can induced by this photon. And also when it emits, it should emit the energy which is equals to the difference between E2 and E1. Okay, so the emitted photon will also have the same energy, and also they'll have the same phase, they'll have the same polarization, and also in the same direction. So this is the important point where it should be, we should be concentrating on. It will have same direction. Okay, and this process is controllable from outside, because if we send the less intense light, then we'll have a less number of photons. But if you send the high intense light, then we'll have a high number of photons. So since the emitted photons will move in the, sorry, what happened? Yeah, since the emitted photons are in the same direction, then what happens is, now this particular photon, a single photon emitted two photons, right? Now what happens is, since these two photons are in the same direction or in the same phase, now these two photons also tend to interact with the other atoms which are in the higher energy level, and they'll tend to, again, these two photons interact with two more atoms. Okay, now what happens is, then they'll release 2 plus 2. Okay, they'll release four photons. Okay, which has all these four atoms, photons will have same energy, same phase, same same polarization, and also they will be in the same direction. Okay, so this is how they'll try to multiply. So the multiplication of photons takes place in this stimulated emission. So the first, there will be one photon which interacts with one atom which is in the higher energy state and produces two photons. Now these two photons, in their direction, on their way, they'll interact with two other atoms which are in the higher energy states and produces four photons. Okay, now these four photons, each photon will generate two more photons. Okay, these four photons interact with the four atoms which are in the higher energy state, and they'll tend to increase the number by 2. So each photon will give rise to two photons. So now there will be four photons will generate 8 photons. So like that, if there are n number of photons at the end, so we'll generate, it will be 2 power n. So you can see that the multiplication happens in this manner: 2 power 0, 2 power 1, 2 square, 2 cube, and then finally 2 power n. That's where there is n, if n is the total number of atoms in the higher energy states, then there will be 2 power n photons will be generated. Okay, so that's what it suggests is, these electromagnetic waves of extremely high amplitude could be generated by the combined stimulated emissions from a large sample of atoms, leading to amplification of light. Now, since all these photons are in the same phase, and they have same polarization, they have same energy, now there can be a constructive interference between these photons. Okay, there will be constructive interference, and because of this constructive interference, we know that constructive interference, the amplification, the amplitude of the wave increases. So since here, because of this stimulated photons have the same phase and they are in the same energy, there will be a constructive interference, and this interference gives rise to a very high intense, because they're in the same direction. And there will be 2 power n number of photons will be there, and all this, when there is a constructive interference, then there will be a final resultant wave will be have very high intensity. Okay, so the constructive interference of many waves which are in same phase traveling the same direction with common frequency produces an intense coherent light beam. Okay, coherent means they'll have the same frequency, right? So we are talking about common frequency. All the photons will have same frequency, so there will be a high intense coherence light beam. The resultant light is a single plane wave in which all of the individual waves emitted by the individual atoms have combined in one phase. So in graphical form, we can see here like this. So all there are coherent waves. These are the coherent waves. Okay, they'll have a constructive interference, and this is like a three dimension. We are talking about three dimensions. So these are the three components of the resultant wave. So the final wave will have a high intense, high amplification, and high intensity because of the constructive interference. And this amplitude is proportional to n, that is the number of atoms in the medium, and the intensity will be proportional to the number of square of the number of atoms, that is intensity is proportional to n square. With this is not possible with the common light. Okay, this is the, we cannot explain this whole process in the quantum mechanics in classical mechanics. That is, energy is given by the, here what is the that first we started with the energy. There are two processes can happen, that is light can give energy to the atom and atom can give energy to the light, okay, to the radiation. So that is not explainable. We cannot explain this on the basis of quantum mechanics, but here because of quantum mechanics, in quantum mechanics the energy is discretized. Okay, so when there is a two energy levels which is having E2 and E1, and if we have a photon which is particularly a photon which has a energy which is exactly equals to the energy level, the difference between the two energy levels gives rise to another photon, that is this. Here the energy is given by the atom. Okay, so we are giving the energy is given by the atom to the photon, and it produces two photons, because instead of one photon there will be two photons after the interaction, and it gets multiplied and will have a 2 power n number of photons. And these 2 power n number of photons, that is different waves, will have a constructive interference and gives a resultant wave of high intensity and high amplitude. Okay. So I think we'll stop here. We'll see tomorrow. We'll see in our next class what is the differences between spontaneous and stimulated emissions. Okay, it's already 1:30, so we can stop here. So are there any doubts as of now? What is n? So in n is the number of atoms in the higher here in 22nd slide. So n is the number of atoms in the higher energy state. So here we are talking about energy levels, right? So if there are n number of atoms in the higher energy state, so that many atoms will interact with the photons and results in a 2 power n here, right? So that is what n. Okay, the number of atoms in the higher energy state. What is constructive interference? So interference, there are two ways. So if there are, interference, right? Interference is nothing but mixing of waves. When these two waves are in same phase, then what happens is simply amplification the amplitude of the two waves increases. The resultant wave will have a higher amplitude. Okay, so when two waves are mixing, then if they are in the same phase, then the amplitude, the resultant of the two waves will have a higher amplitude than the initial waves. Okay, that is what we call constructive interference. If they are in out of phase, then there will be a destructive interference. Okay, so if they are two out of phase, then the amplitude of the resultant wave will be less than the two individual waves. Okay, so this kind of mixing is called, if the amplitude is increasing, then that is we call a constructive interference. If the amplitude of the resultant wave is less than the individual waves, then we call it as a destructive interference. And sometimes if it is completely out of phase, then there will be no resultant wave at all. Okay, so that's what we call destructive interference. If the amplitude of the resultant wave is higher than the individual waves, then we call it as constructive interference. When they are in the same phase, this happens only when they are in the same phase. So here, all the photons are in the same phase as the initial photon. So there will be a compulsory there will be a constructive interference, and the resultant wave will have higher amplitude. And amplitude is neither intensity is proportional to amplitude, since intensity is proportional to amplitude, square of the amplitude. So here intensity will be proportional to n square. Okay. So any more doubts? Are you clear? Q5, I think. Okay, good. So if there are no doubts, so I'll end the session here. But, how many are there? 54. So I'll for as of now, I'll just take take the attendance for now. Let me see next time how to calculate this. So K6, I think here I think they are in order. K9, L0, L1, L2, L3, L4, L5, L6, and L7 are not here. L8, L9, M0 is not here. M1, M2, M3, M4.
Suman sir.
M9 and N0 are not.
Suman sir.
N1, N2, N3, N4, N5.
Suman sir.
6, N7, N8, N9, P0.
Sir, it's not able to hear us, sir.
P2, P3, P4, P5. P5, P6, P7, P9, Q0, Q1, Q2, Q4, 5, Q6, Q7, Q9.
Suman sir.
R0, R1, R2, R4.
Kalyan sir, Basha sir is calling you, sir.
Okay.
Sir. Suman sir.
Others who have registered with your name, okay, I'll just P0 is here, N5 is here, L7 is here, N5 is also again present, L7, P0. Okay, M4, M4, Q4, K7, they are present, M8. Okay, so as of now, I'll just stop here. Okay, I'll end the meeting here, I guess. I can end the meeting here.